Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH and the equilibrium concentrations of all species present for a solution containing a weak acid and the conjugate base of that weak acid present as a common ion. In this specific problem, we're asked to calculate pH and the equilibrium concentrations of all species present in a solution of 0.30 molar ascorbic acid and 0.25 molar potassium ascorbate. The first thing you want to do is to identify the species present initially and their acid-base properties. So we know that one species present initially is ascorbic acid, and we know that ascorbic acid is an acid. So that is one species present and its acid-base properties. Another species present is potassium, and we know this because when potassium ascorbate dissociates in solution, it gives a potassium ion and the ascorbate anion. Potassium is inert, so potassium is one of those cations that come from a strong base that do not react appreciably with water and therefore does not participate in the acid-base chemistry or change the acid-base properties of a solution on its own. Another one of the species present is the ascorbate ion. So that's C6H7O6, and this is the conjugate base of ascorbic acid, so we know then that it acts as a base. And finally, another species present initially is water, and water, as you know, can act as both an acid or a base. So the next thing you want to do once you've identified all the species present and their acid-base properties is to identify the possible proton transfer reactions so that the principal reaction, which is the reaction that will head the ice table, can be identified. In this case, there are two acids and two bases. And because of this, it means there are four possible proton transfer reactions. The first one will be the case where ascorbic acid donates a proton to water to give the hydronium ion plus its conjugate base, the ascorbate anion. The Ka value for this reaction is 8.0 times 10 to the negative 5. This is something you could look up in a table of acid dissociation constants. And remember, the reason we're identifying all these possible proton transfer reactions is because we're going to pick the one with the largest Ka value to head our ice table. Another possible proton transfer reaction is where one of the water molecules acting as an acid transfers a proton to another water molecule acting as a base, and you're left with a hydronium ion and a hydroxide ion when that happens. And the Kw value for that equation is 1.0 times 10 to the negative 14th. Another possible proton transfer reaction between an acid and a base is when ascorbic acid donates a proton to ascorbate its conjugate base, which are both present in solution initially, to give you the ascorbate anion, which is what's left over from ascorbic acid when it donates a proton to the conjugate base reactant, plus ascorbic acid. And this is what's left over when this conjugate base, that's the reactant, receives a proton from ascorbic acid, which is the other reactant. So the K value for this, because we have the same products and the same reactions, is going to be equal to 1. And the final possible proton transfer reaction between an acid and a base is one where water is acting as an acid, and we have the ascorbate ion acting as the base, where water transfers a proton to ascorbate to give ascorbic acid plus a hydroxide ion. And the K value for this is very, very, very small, because ascorbic acid is a much stronger acid than water, so most of the proton transferring in this solution will be happening according to this first reaction here. So we can eliminate the fourth reaction as a possible proton transfer reaction that will head the ice table. We can also eliminate the third reaction here, which has a K value of 1, because even though it has the largest K value, it's not going to change any of the concentrations. And remember, in our ice table, the second row labeled C indicates the change in concentration in terms of X. So we need an X to solve for, and if there's no change in concentration, then we won't be able to solve this problem to find the pH and the equilibrium concentrations of all the species present. So that eliminates the third reaction written here as the principal reaction that will head the ice table. And then we're left with the last two, and the first one, showing proton transfer from ascorbic acid to water, has the bigger Ka value, so this is going to be the reaction that heads our ice table. So now we can draw the ice table. So we'll put our principal reaction at the head of the ice table, ascorbic acid transferring a proton to water to give the hydronium ion plus the ascorbate anion, or the conjugate base of ascorbic acid. Then we have our three rows: the initial concentrations, the change in concentrations, and the equilibrium concentrations. So we're given, as part of this problem, that we start with a 0.30 molar solution of ascorbic acid. So the initial concentration of ascorbic acid will be 0.30. The initial concentration for the hydronium ion is approximately equal to 0. There's always a little bit present, but there won't be much present until the ascorbic acid starts to transfer protons to water. And then for the initial concentration of the ascorbate ion, we're told in this problem that we start with 0.25 molar potassium ascorbate. So we have as our initial concentration of this ion 0.25 molar. Because you can see, based on the reaction stoichiometry showing what happens when potassium ascorbate dissolves in water, we have a 1 to 1 to 1 molar ratio here, so that for every mole of potassium ascorbate that dissolves in water, we get 1 mole of the ascorbate anion. So if we have 0.25 molar potassium absorbate, we also have 0.25 molar ascorbate ion. So now we're going to define X as the concentration that's lost of ascorbic acid when it starts to transfer protons to water. And specifically, X is the concentration that's lost to reach equilibrium. So for every mole of ascorbate that is lost due to proton transfer, 1 mole of hydronium ion and 1 mole of ascorbate anion are gained. So on the product side of the change row, we'll have plus X and plus X for the concentration change of the products. And now we can write the equilibrium concentrations in terms of X. We have 0.30 minus X for ascorbic acid, X for the hydronium ion, and 0.25 plus X for the ascorbate anion. So now we can use the Ka value for the equation that heads the ice table in order to solve for X. So the first thing we're going to want to do is write the equilibrium equation. And the equilibrium equation is going to be Ka is equal to the concentration of the hydronium ion plus the ascorbate anion divided by the concentration of ascorbic acid. We can substitute in our values here and say that Ka is 1.8 times 10 to the negative 5. The hydronium ion concentration in terms of X is equal to X. The ascorbate anion concentration in terms of X is 0.25 plus X. And the ascorbic acid concentration at equilibrium in terms of X is 0.30 minus X. So here is the expression describing the concentrations, the ratio of products over reactants at equilibrium. So the next thing we want to do is to try to get rid of these two X values, because if we can get rid of those, then solving this problem becomes a lot easier. So we're going to make an assumption. We're going to assume that 0.25 plus X is approximately equal to 0.25 and that 0.30 minus X is approximately equal to 0.30. So what we're really saying in both of these cases is that the X value is so small that adding it to 0.25 or subtracting it from 0.30 is not going to change those initial concentrations of 0.25 and 0.30. So let's test that assumption. To test the assumption, we're going to go back to this equation here and just get rid of those X's, solve for X, substitute X back in here to see if this assumption actually holds. So we have 1.8 times 10 to the negative 5 is equal to X times 0.25 divided by 0.30. Divide or multiply both sides by 0.3, you'll be left with 2.4 times 10 to the negative 5 is equal to X times 0.25. And then divide both sides by 0.25, you'll get X being equal to 9.6 times 10 to the negative 5. So now we've solved for X and we can substitute it back in to these two expressions to see if it makes a difference, if it will change the 0.25 and the 0.3. So we're going to add 0.96 times 10 to the negative 5. When you do the math there, you're left with 0.250096, rounding that to two significant figures, you're left with 0.25. So adding X to 0.25 does not change the value of 0.25. And you'll find the same thing here. Subtracting X from 0.30, and the X we found is 9.6 times 10 to the negative 5. You do the math here, and what you get is 0.2999904, rounding to two significant figures, and you get 0.30. So subtracting X from 0.30 does not change the value. So it's okay to make this assumption, and we've already solved for X. So now we can use this X value to find the concentrations in our ICE table. So the hydronium ion concentration we designated as X, so the equilibrium concentration in the last row of our ICE table. And we know that the hydronium ion concentration is 9.6 times 10 to the negative 5 because it's equal to X. Now to find the other two concentrations that are in our ICE table, the ascorbate anion concentration we've designated in our ICE table as 0.25 plus X. We've already seen from testing the assumption that adding X to 0.25 does not change its value. So our ascorbate anion concentration is 0.25 molar. And then we're also interested in the concentration of ascorbic acid. Running out of room here. Move this down a little more. And in our ice table, we designated the concentration of ascorbic acid as 0.30 minus X. And we've already seen from testing the assumption here that subtracting X from 0.30 does not change its value, and you get 0.30. So we found the concentrations of 3 of the species present. We also need to find the concentration of hydroxide ion, because that's another species that is present. So we know the relationship Kw is equal to the hydronium ion times the concentration of the hydroxide ion. Rearranging things here, we know that the concentration of the hydroxide ion is equal to Kw divided by the concentration of the hydronium ion. You've already found the concentration of the hydronium ion, so you can say 1.0 times 10 to the negative 14th divided by 9.6 times 10 to the negative 5, and that will give you 1.0 times 10 to the 10 molar. So there's our concentration of hydroxide ion, and the last thing we need to do here is solve for pH. So you know that pH is equal to the negative log of the hydronium ion concentration. So we have the negative log of 9.6 times 10 to the negative 5, because this is the hydronium ion concentration that we've solved for here. And when you do the math there, you find that the pH is 4.02. So that's it. We've solved for the pH and the equilibrium concentrations of all species present.